Hello everyone. In this video we're going to study examples from chapter 6, which is all about sampling distributions. My name is Fred Rispoli and I'm coming to you from Stony Brook University. The overview for this video is we're going to start out talking about the central limit theorem and then look at sampling distributions for our sample mean. We'll look at examples 1 and 2 that cover this. In example 3, we're going to take a look at the sampling distribution for one variance, also known as the chi-square distribution. And example 4, we'll look at sampling distributions for the ratio of two variances. This is known as the F distribution. These examples are chosen based on frequently asked questions by students and frequent errors on test results. So let's begin with the central limit theorem. This is one of the most important theorems in mathematics and certainly the most important theorem in statistics. The central limit theorem tells us about the distribution of a sample mean. A good way to think about this is if you have a data set, doesn't matter what the properties are of the data set, but if you just have a data set and you keep taking samples of a fixed size, we'll say size n, and calculate the sample mean x bar, so we're doing this repeatedly over and over and over again, then eventually a distribution will be formed, and the distribution, turns out, follows a normal distribution, right? So the central limit theorem tells us that if the size of each sample is n, and n is at least 30, then the distribution of the sample means is approximately normal. Now, we'd also like to know what the parameters are for the distribution of sample means, okay? And the first one is sort of easy to guess. If the underlying distribution has a certain mean, then the distribution of sample means has the same mean. But that's not the case for the standard deviation. Okay? If the underlying distribution has a standard deviation sigma, then the distribution of the sample means is equal to sigma divided by the square root of n. So this is an important term that you'll see over and over again in the next few topics that we study. We could create a more formal statement. The formal statement is if x1 up to xn is a random sample from any distribution with mean mu and variance sigma squared. And then if n is large, right, in particular, greater than or equal to 30, then when we look at this random variable z given by the sample mean minus mu over sigma over the square root of n, this is approximately normal with mean 0 of variance equal to 1. So this follows a standard normal distribution. Yet another way to think about the theorem is visually. Let's take a look at what happens as the sample size gets larger. Okay. Well, if we start with a normal distribution, okay, and you just look at individual values in the distribution, we'll see this would be the graph. Okay. If we start looking at samples of size 2 and we graph the sample means, you could see this is the graph. Doesn't look too much different, but it actually gets just a little bit thinner than the first one. If we started out with a uniform distribution, right, and just looked at the values, we would expect some sort of rectangular shape over here. But when we look at subsets of size 2, let's say we add up values and find the mean, then when we graph that, we would get a triangular distribution. If we start with an exponential, we would expect something like this for an exponential distribution. But if we now look at taking samples of size 2, so I'm taking 2 values and I'm finding their average. Now we plot them, you could see the shape of this curve changes quite a bit. And even a parabolic distribution, something like this, if we start taking values, we add 2 and then find their means, you could see this changes quite a bit. So now, what happens as the sample size get larger and larger? Okay. Well, if we go down this column with the uniform distribution, so sample size 2, we get a triangle. At sample size 5, you can see we start to get something that looks normal. And then at sample size 30, we definitely get this bell-shaped curve behavior. So here we're starting with uniform, but when we look at the sample means for samples of size 30, we hit normal. Exponential. We start out with this sort of exponential decay curve. You could see when n is 5, starts to look a little bell-shaped, but when n is 30, there's no doubt about it. This looks like a normal distribution. And similarly, when we start out with the parabolic, we see, now this doesn't happen quite as fast, right? At 5, it still does not look normal, but once we get to 30, it does have that normal distribution behavior. All right, let's take a look at some examples where we can use some of the results of the central limit theorem. Suppose the amount of time that a 10-year-old boy plays video games in a week is known to be normally distributed with mean of 10 and standard deviation 4 hours. Now let's say we choose a sample. Suppose we choose 9 10-year-old boys chosen at random, and we ask, what's the probability that the sample mean time for playing video games is between 8 and 12? Okay. Notice it's a little different from the type of problem we looked at in Chapter 4. Chapter 4, we might have said, suppose we pick one boy at random. What's the probability they play between 8 and 12 hours per week? But here we're saying, all right, we're going to choose a sample of 10. What's the probability the sample mean is between 8 and 12 hours? All right, so let's take a look at that. We'll come back to B in a minute. So we could set this up. We think of picking nine boys at random. Okay, we're interested in the probability that X bar is between 8 and 12. So now we could set this up the way we did in Chapter 4. But in Chapter 4, we wouldn't have this other adjustment down here. Okay. Since we have a question about a sample mean, the correct standard deviation is 4 over the square root of 9. That's what we get from the central limit theorem. Okay. We also know from the central limit theorem that the sample mean follows a normal distribution. So we can now approach this as a normal distribution problem. Here we get 8 minus 10, so we have 8 here. It's 8 minus the mean. Remember, the mean was given right here, the mean of 10 hours. So 8 minus 10 over our adjusted standard deviation. 12 minus 10, same adjusted standard deviation. So these simplify to 1.5 here. This is going to give me my positive 1.5. This will give me my negative 1.5. So I could find my probability using a normal distribution table. I have phi of 1.5. So we could check out our table where we have positive values for z. So 1.5, this column gives me 1.50. So we would get 0.9332. Okay, so that's how I get this value right here, my phi of 1.5. 0.9332, and then I have phi of minus 1.5. So there I need the normal table with negative z values. So minus 1.5. So I get 0.0668. work out the subtraction. My final answer is 0.8664. Okay, so that's part A. Now part B, we're told, suppose a boy is considered addicted if he plays computer games for more than 16 hours a week. If we now take 12 10-year-old boys chosen at random, what's the probability at least one boy is addicted to video games? Okay, so at least one boy, well, that should start to get you thinking. Usually when you have a question where it says at least a certain amount, it's good to think about the complement. So here's what we're going to do. Sort of two problems in one here. The first thing is we're going to figure out the probability a boy is either, addicted or not addicted. So let's let X be the number of hours a 10-year-old boy plays video games. So we need to figure out the probability. Just an individual is addicted. So we're going to calculate the probability X is greater than 16. Since this is now just an individual probability, we do this the way we did things in chapter 4. Find the probability Z is less than 16 minus 10 over 4. So this is X minus mu over sigma. That simplifies to 1.5. So instead of doing the greater than probability, we use the complement. We do 1 minus phi of 1.5. We looked that up a minute ago. So we got 1 minus 0.9332. So we have this 0.0668. That's the probability a boy is addicted. And you could see we have the 0.9332 is the probability that they're not addicted. Now, to answer the question, if we pick 12, what's the probability at least one is addicted? Well, now we define a new random variable y. We'll let y be the number of 10-year-old boys who are addicted to video games. Okay, so y is the number addicted. Now remember, this is out of 12, and the probability of an addiction is 0.0668, which you calculated over here. So the question asks, what's the probability y is greater than or equal to 1? Well, once again, it'll be easier to use the complement, right? I want 1 minus the probability y is equal to 0. If we were to do this sort of without the complement, you'd have to figure out the probability exactly 1 is addicted, exactly 2, exactly 3, and so on. Much faster to do it this way. So the probability that none of the 12 are addicted, we could get by thinking in terms of 0.9332 is the probability that one boy isn't addicted. But if I have all 12, and we're assuming an independence, the probability that none of the 12 are addicted is 0.9332 to the 12th power. So we could work out this calculation 1 minus 0.9332 to the 12th. All right, this expression simplifies to 0.4362. Do the subtraction, we get our answer 0.5638. So again, you're picking 12 at random. The probability at least one is addicted, you could see here, is about 56%. Okay, so that concludes example 1. On to example 2, another example involving the sampling distribution for x bar. Suppose we have a random variable x from a population that has a mean of 70 and a standard deviation of 15. A random sample of 64 is selected from that population. Notice no other information is given about this. right? We don't know if this is normal, exponential, or something else. But it doesn't really matter because we have a sample of size 64. And we're asked to find the distribution of the sample mean of the 64 observations, and then use that answer to find the probability that a sample mean will be greater than 75. So we know by the central limit theorem, the sample mean is approximately normal, mean 70, right? The mean just matches the underlying, but the standard deviation we have to adjust. The standard deviation would be, we could think of it here, either 15 over the square root of 64, okay, or this is given here as the variance, 15 squared over 64. When we take the standard deviation and just simplify the fraction, we get 1.875. So we could express this either in words, the way I just went through it, or using the n notation. We would say the distribution is normal. So the capital N is for normal. 70 is the mean, and this is the variance. We know we have 15 squared over 64. For part B, we're interested in the probability a sample mean out of this underlying set is greater than 75. So we know x bar is approximately normal. So we could approximate this by finding the probability. Z is greater than 75 minus my mu is 70. And this is the adjusted standard deviation, right? We took care of that up here. So we have 1.875. So this fraction simplifies to 2.67. We have a greater than probability here. Easier to convert this using the complement. So this is 1 minus phi of 2.67. So we need to look up 2.67 in a normal distribution table. And if we go back to our tables, we need the one with the positive z. This blue circle over here I use to at least get as close to the 2.67, right? So I look for 2.6 here, and I get the row, so this brings me to the right row. And then my second decimal place is 7, so 2.67 right here. My probability would be 0.9962. Oops. So 0.9962 we have over here. So I work the subtraction. Our final probability is 0.0038. So you can see there's just a very small probability that the sample mean will be greater than 75. Okay, so that concludes example 2. Next, let's take a look at an example involving sampling distribution for a variance. Suppose we know that the variance of a normal population is 4. We're asked, what's the probability that the variance of a random sample of size 10 exceeds 6.526? So we're asked to identify the correct distribution. So find the probability, go ahead and find the probability using the correct table. Confirm the probability using R, and let's sketch a graph of the probability. All right, so we have a question involving the variance. We know the distribution we need is called the chi-square. So chi-square is given by n minus 1 times the sample variance divided by the population variance. So we could fill some of these values in. We know n, our sample size was 10, so n minus 1 is 9. our population variance is equal to 4. So we get 9s squared over 4, 9 degrees of freedom, chi-squared distribution. All right, so this will sort of point us in the right direction in terms of what table to use and where to look in the table. Now in part B, we want to know the probability that a sample variance is greater than 6.526. Okay, so we could think of this, we want to sort of convert this into this chi-square value. So we could start off, in a sense, we could multiply by 9 and divide by 4. So we get the probability 9s squared over 4 is greater than 9 times 6.526 over 4. Okay, but we know over here this is chi-squared. Right, this simplifies to chi-squared. And then on the right, when we work this out, this simplifies to 14.68. So the probability we want is equal to the probability chi-squared is greater than 14.68 with 9 degrees of freedom. So this 0.10 is obtained from a table. Let's take a look at how we would find that. So here's a chi-square table. We would start out with the degrees of freedom. Okay. So my degrees of freedom is 9. And I would sort of scan through this and look for my value. Right? Sometimes you'll find the value exactly what you want. Other times you might have to sort of use bounds, but here we find it exactly. We get 14.68. So the probability that chi-squared is more than this value, okay, we could come up here and read it off the table, is 0.10. So that's how we get to 0.10. The probability chi-squared greater than 14.68 is 0.10. Okay, we could confirm this in R, okay, but you have to remember that R gives you CDFs, cumulative distribution functions, and we want a right tail probability. So my code in R would be 1 minus P chi-squared, and P is for cumulative. This is my value for chi-squared. This is where we would enter that 14.68. And the second input is the degrees of freedom. You can see we're getting, well, roughly 0.10 would be your output in R. To help visually see this, I put together something called a distribution plot in Minitab. Okay. So here we'll obtain a graph of the chi-squared curve for degrees of freedom 9, and the probability is shaded. So we have the distribution plot. Here's the curve. It's a little bit skewed. Okay. I enter 14.68 for my chi-squared. It shades this right tail and gives us the probability. Again, you can see this is 0.100, and this was rounded off a little bit. So that's what this looks like. Okay, so that concludes example 3. In our last example, we're going to take a look at the F distribution. The F distribution most generally appears in tests where the null hypothesis is that 2 independent normal variances are equal. Then their ratio is examined to see if this is significantly sort of incompatible with the null hypothesis. Or in other words, if the ratio between the two variances gets very, very large, then we know that the variances are not equal. The closer that ratio is to 1, the more likely it is that we have two equal variances. Now, something that makes the F distribution a little different is that this requires 2 degrees of freedom, and typically the graph is skewed. You can see some different cases over here. These are your degrees of freedom. You can see when they're both 1, we get this shape over here. If one is 2 and the other is 1, we get something like this. And you can see just how these curves really change dramatically based on the degrees of freedom. So here's an example. Let's say we have 2 independent random samples are obtained from normal populations with equal variance. If the sample sizes are 5 and 7, it's supposed to be a 7 here, perform the following calculation. We want to know the probability the ratio of the 2 variances is greater than 6.23. Let's use an F table and confirm the answer using technology. Okay, so we must use degrees of freedom equal to 4. We get 5 minus 1, and this value that's supposed to be a 7, 7 minus 1 is 6. So you can see that when we work out this probability that we want, okay, you'll see that we'll get an answer of 0.025. But let's go through this over here. So I have degrees of freedom. Right? Remember, I had a sample size 5, degrees of freedom 4 here, and we had sample size 7, degrees of freedom 6 over here. I want the probability that my ratio is greater than 6.23. Okay, so I would sort of look over here. I have different probabilities, and you can see here, this is sort of the value you would get from the cumulative PDF, and then this would be 1 minus that value, so this would be the right tail probability. I'm going to be calling that alpha a lot in the next few chapters. So we get an answer of 0.025. If we wanted to try to visualize this, you could see here that, again, using a Minitab distribution plot with degrees of freedom 4 and degrees of freedom 6, the graph we get from the F distribution, you could see highly skewed, where my value is 6.23 here. We get the shaded area to the right represents the probability, and I have rounded off here. You see we would get 0.025. So again, these values and use of the F distribution we won't see again until we get to chapter 9, but when we want to test to see if 2 variances are equal, it will be based on the F distribution. Okay, I hope you've learned something from this video. We've reached the end.